Our next speaker is Monsieur Jean-Yves Vion-Dury from Xerox Xerox Grenoble. Is that right? Yes. Sorry, it was just a reflex to add the syllable park after the. He works for Xerox in their laboratory in the beautiful south of France with all those mountains. So, Jean-Yves, are you ready?
Almost.
Almost.
Okay. This one. Well, I will present today theoretical work on a generic calculus for XML deltas. So indeed, I'm working in Xerox Research Center Europe in Grenoble, and we have several activities there. You can see the detail here, and you can get more detail using the URL here. I'm personally involved in the Service Innovation Lab and more precisely in the document structure group. Well, I will try to present you key points to capture this work. My goal is not to develop, of course, all the content of the theory, but to explain the most salient part of the calculus, to give you the basic formal tools. And we speak a bit about atomic deltas, composite deltas, where there is much innovation. I will give some perspective on applications and quickly conclusion. Okay, so here we describe a simple transformation applied on a string, and you see that you have several steps where we use a designation mechanism based on integer. And two simple operations, deletion, insertion, as you know, to transform an input string into a result string. So we can compose all this operation together using the semicolon operator here and get this more compact notation with the same meaning. Now, what's interesting to observe is that we cannot switch the various elements of this composition. If we do so, for instance, here, if we put the first del operator on second position, we obtain a different result here. And that's in fact a fundamental problem when you want to manipulate such expressions. Instead, if you want to do what you wanted to do, I mean to switch the first operator, you have to relocate some of the other instructions here. It means that we do not have an obvious and an intuitive equality, and we do not have a generic commutativity here. That's captured in the calculus. The transformation itself is defined through an abstract operator, which is a patch, which allows to apply the operation on document D here, the first argument. This equation, in fact, is logical notation. On the top, you have the condition, the hypothesis, if you want, and it says here that the composition of deltas must be well formed. That's the condition. And below, you have the definition itself, and it says that the patch operation, in fact, is defined as, in fact, the subsequent application of the two deltas. So you apply delta 2 on the result of the application of delta 1. That's this captures the dependency, in fact, exactly. Now we will look at another case, interesting, where, in fact, you have what we call a dead path, in fact. You see two intermediate stages here, where we transform the input string, and finally we result in the same string. It means that some of the intermediate operations were not necessary, in fact. And this is a problem, because what we would like to do is to detect such situation. So we would like to prove that both are equivalent from the operational point of view. And moreover, we would like to prove that on a systematically basis, which is more difficult, not on this particular case, of course. In fact, reasoning is not difficult, it's quite natural activity, you see. Before, after scheme, we see that, I mean, everywhere. So it's not, this talk should not be that difficult to hear and to understand, I hope so. Well, so some key points. Working on trees is much more difficult than strings. Yeah, I show you the first example on strings, but it's more difficult with tree because you will see, we will develop that later. And also, when you try to build a calculus, the true challenge is to keep it simple. And you constantly have to reduce the first proposal you had, your intuition, to something more simple. This work today is not about constructing differences and difference description. It's not about building diff algorithm, which is a well-explored field. It's really about understanding the very nature of delta scripts, which is not, to my knowledge, is not well done yet. And indeed, simplicity, beauty. I love this picture. It's from an artist from Paleolithic, I think so, and it's extremely simple and extremely beautiful. And for delta transformation, usually we can describe this transformation using two primitive operations. In my case, I need one more, this knob operation, which does nothing, but is quite useful in handling equational properties. But still, it's very simple as the basis. Now, if we go to handling trees, and we want to generalize the example I gave you so far. Here we have simple trees, noted using a linear notation here, with a node A, two children, B and C, and you see the leaves, Google. Well, this transformation, in that case, will be rewritten this way using a structured path instead of simple integers, but with the same meaning, except that, in fact, you will see, I will show that doing so, you add more information, and we can use that. So the first remark is that, in fact, we need now a designation mechanism more complex than just integers. And so we define a pass language based, here is a simple grammar rule. It's based on integer and the composition of them on the right part. And here I wanted to keep the notion of having attributes, such as in XML model, because it's difficult to handle generally in theoretical calculus because it's a non-ordered part of the tree. And if you forget that, you have trouble when you want to generalize your result to real life application. But still, it's simple yet. Well, regarding the interdependency of nodes when you deal with trees, we distinguish three cases. The first one is when you have, in fact, independence. Due to the topology of tree, you can swap operation without problem, what we call orthogonality. The second one is when you have, in fact, two subtrees which are embedded. And the third one, you have a specific dependency, which we characterize as a sibling dependency. And on these three different cases, we propose three composition operators to handle them. But first, we need some powerful tool to reason on path. And so we came with four mathematical relationship for path. The first one is the embedding itself. It's quite intuitive. Right? You say that trees are in fact embedded. It's a irreflexive relation, asymmetric and transitive. The second one, total ordering, in fact, is well known in, for instance, in XML processing. It's ordering which allows you to consider that whatever node you have in your tree, it can be compared with whatever node. It's the reading order node, in fact, of tags in an XML document. The third one is more specific here. It's sibling dependency, and this one is really important because it captures exactly the dependency we want to understand and to master. And the third one, the orthogonal operation, is also important for the commutative composition, which we call parallel composition. And on the bottom part here, you see you just have an example of how we can use logical definition of operators to prove and to assess such relation in a logical way. Rather simple, in fact. Well, now we understand that with path we will need some formal operation to handle relocation when you want to swap operation. So what we did is to define low-level algebraic operation on path. And I give you an example on the right column of how it works. So you see here what we add with respect to the depth of the operand here. So adding 1 to the second level, it gives 1, 3, 3, starting from 1, 2, 3. Same symmetric example with subtraction. And the last function is a function that allows us to capture the signature, if you want, the depth of the operand. And together, it's really useful to propagate the modification when you use operation on path. See? Well, in this contribution, what we propose is to distinguish 3 different composition operators: sequential one, concurrent, and co-referential. And that's new up to our knowledge. We also define formally transposition operation, and we propose an equational system to reason on the equivalence, as I presented in the first part. So these composition operators here, again a grammar rule which defines the syntax of the formal language. The first small delta is in fact the any atomic operation, one of the 3 I showed. The second one is a standard sequential composition. Then you have with a diamond, which is a concurrent composition, and the last one, which is the most difficult to probably to understand and to capture, is a co-referential composition. So the parallel composition just says that, very simply, that in fact it allows to be considered as a sequence of 2 deltas in any order. No sensitivity to order. You can commute. And here, for instance, we can rewrite the previous transformation in such a way that we can exhibit this diamond operator. You see, what it means is that left part and right part can be executed independently in any order. And it's interesting because doing so, you inject information, in fact, in your expression. And this information can be used, it has value, it can be used later for other transformation. The snapshot composition, or the co-referential composition, I will explain a bit later, but here you see that in some case, in order to apply this operator, you need to have a specific dependency between paths, between deltas. And if they are orthogonal, it's the last line, then it's the same operator than for parallel composition. And moreover, you can see that we use another transformation on the right part of the operand in the first two equations on the right. And that's, in fact, the notation for relocation. I won't go much in detail for this relocation operation. You can find details in the paper, of course. What I would like to show is that we can so transform the same operation. Here you see that the tree is a bit different because the GUI of Google now is in the first subtree. So that, in fact, we can show the impact of using a co-referential operator here. You see that the 1, 1, 3, the del 1, 1, 3, which was the second operation, now has been rewritten as if, in fact, the referential is kept unchanged. That's the key point here. In the first case, you consider that it has changed, of course, because you deleted the first element. And in the second one, you consider that both are independent and are talking about the same referential element. Okay. So, application of these operations. First, the computation of normal forms, which is a way to eliminate the dead paths, such as shown in the first part of the talk. Well, we would like to be able also to transform the delta scripts for specific purposes. For instance, if you have a dedicated patch engine, in-memory patch engine, for instance, you would like to put the emphasis on move operation because you have in-memory with pointers, it's quite efficient to do so. But if you are in a streaming environment with Sax event, for instance, so you will probably organize the delta script differently in order to capture and to stick to the temporal organization of events. And the parallel composition also could be applied to conduct, in fact, parallel modification of big trees on a parallel machine, of course, or parallel architecture. Now we would like also perhaps to transform the scripts in order to add information directly and to gain some time and some efficiency in processing. And also probably there will be a new application for difference computing. We cannot understand now, but I mean thinking about temporal synchronization when you have either infinite streams or you have a very, very huge document distributed or replicated on a network, for instance, and so on. And document can be really huge. See, that exists. Incredible. Okay, so remember our problem of equivalence in that case with the dead path. Here I suggest a normalization method which is based on reordering the different operation on two criterions. The first one is order of pass. So we will try to put lower pass in first position. And when you have insertion and deletion operation on the same pass, you try to swap them. Two criterion. So we start from this end, and you see when it's underlined is operand we try to swap. The first line you see is del 3, and we swap, and this becomes by relocation del 4, and so on, and we converge to a normal form here on the bottom. And if we do that on the longer script, you see that slowly but surely, in that case at least, we will reach the same normal form. And that's the basic idea of building a general equivalence. So as a conclusion, the calculus captures the dependencies derived from topology properties of trees. The composition operators are novel. Of course, two of them are novel. The sequential is well known. And this increases expressiveness of the calculus. And we also can, with the same theoretical tools, reason on standard string-based editing deltas. So future work, you see, exploring. I must say that I'm not entirely happy with the calculus today because it's not possible to model a move operation in a satisfying way, especially regarding the normalization process. So I have some idea to explore there. To build and characterize an algorithm for normalization that would be very useful and doesn't exist to my knowledge. Well, implement some practical tools and to demonstrate and perhaps to interest some other people around. And why not exploring novel application domains? And yes, that's it. Thank you.
We have a few minutes for questions.
Hi, thanks. So I understand that you're not interested in, or you said at the beginning you're qualified at not building a difference engine. But in many cases, we're faced with a situation where we have two XML documents, where the second one is basically a set of changes that have been applied to the first one, but we don't have the deltas in place. Mm-hmm. A problem that I'm facing in one application is that we've got a lot of annotations that are linked into the first version of the document, and we're looking at various robust linking mechanisms to resolve those annotations in the second one. And I'm wondering whether you've looked at being able to compute the deltas and then apply a calculus like yours to either ease the process of patching those links or to prove a robust linking algorithm as valid or not.
Yes, you're right. That's the idea. For instance, to simplify and to provide the simplest form for comparing a path or transforming the path computed by algorithm, dedicated algorithm, and that's the idea. If you want to use one kind of algorithm for computing the diff, and you want to apply the result using another patch engine, because you can have a different. And then you will need to transform them in a consistent way, and that's also the goal I had in mind. Or more interestingly, if you look at papers around the diff algorithm, very often they come with the idea of optimality, which is really badly defined. Optimality, even efficiency is badly defined because depending on the backend engine you have. You cannot really pretend being more efficient. It could be implementation dependent. If you have a better programmer, then you will have a more efficient implementation. With this kind of tool, you can exhibit, a formal and rigorous definition of what is optimality, in which case.
Other questions?
So as you know, I'm Ethan Munson, for those of you who don't know me. I've had a running interest in XML versioning, and deltas obviously are important in that. And it is really a hard problem to know what the right delta is for a tree. And in my work with Cheng Tao, Cheng has come up with a scheme that's really quite simple. It's very direct. But I think you've been working on this work for a few years now, and I think you may have hit a point where it becomes possible to ask the question, we have a rigorous calculus for this now. Is it useful in a human sense? Is it possible to use this representation to optimize in some sense, to at least shrink in length the descriptions, and then do they answer questions that have human utility?
I see.
And I think that's potentially a very interesting question. I also think there's a question of whether it's a path to some kind of more efficient algorithm, more efficient implementation.
Could be, yes.
And so those at first blush, those are two research questions that I think are interesting, and that you or we or somebody else, Uwe Borghoff's group perhaps, might be able to pursue. So I think I'm really very pleased with where you've been able to come with this, because it's certainly work I couldn't do. So thank you.
Thank you, Ethan.
Other questions?
You talk about normalizing diffs and to find if two different diffs are equivalent, but why not just apply this diff and to see if the result is equivalent? Or you can also compute the diff with algorithm that give you already a normalized diff, minimum diff.
If you want, for instance, you want to build a kind of optimization tool that takes the delta script issuing from another algorithm, well known, and you want to optimize that systematically. You cannot use evaluation for that. You need a methodology to do it, such as you need a methodology to optimize, computer code. I'm not sure to understand the.
Yes, but isn't there already diff that give you a minimum XML?
No. In fact, as I said, the optimality, which is claimed often in papers, is always defined with respect to the model proposed by the algorithm, which is not an absolute criterion. And even often it's the efficiency metric associated with the algorithm is also given in the same framework based on the patch application model they propose. So you do not have this kind of absolute metric of what is the optimal path. And here, if you see, I propose a normalization to reduce the dead path. That's a precise criterion. And but I say that for other optimizations, such as using a particular backend, probably you have to rewrite in other way the diff script to take benefit from particularity of the backend. So there's really something missing in there.
Good discussion. Let's thank both our speakers.
Thank you.